As Sri Lanka embraces renewable energy, solar power has become a key player in the country's clean energy journey. But with this growth comes a challenge. The grid isn't always ready to handle the power that solar provides. During peak sunlight hours, solar generation often exceeds what the grid can handle. Without the right infrastructure, this surplus energy leads to voltage spikes and ultimately gets wasted. A grid-level battery energy storage system, or BESS, changes that. BESS captures the excess solar energy and stores it to be used when it's most needed. This prevents energy waste, keeps the grid stable, and ensures a reliable supply of clean energy, even when the sun isn't shining. When demand is high, like during busy evenings, BESS can discharge stored energy, relieving stress on the grid, facilitating demand response. This reduces the need for costly infrastructure upgrades, keeping energy affordable and accessible. BESS is also a reliable backup during power outages. For critical infrastructure, like hospitals and emergency services, BESS ensures that life-saving equipment and essential services remain powered. BESS can even power critical loads at residences.
Introducing Lifeline Power, a revolutionary way to ensure uninterrupted energy for your home or business during power outages. With Lifeline Power, we provide energy packages that can be pre-purchased and kept as a backup in case of a power outage. There are two types of power outages, planned and unplanned. For both types, Lifeline Power offers tailored energy packages. Planned outage packages are designed for scheduled outages. Consumers can purchase these packages in advance, knowing when the outage will occur. For unexpected outages, there are unplanned outage packages. These work like insurance. Customers can purchase a package that covers energy use during unforeseen outages. When an outage occurs, our system receives a signal from the utility. It then sends a list of smart meters to be activated. The utility connects the battery supply to these specified meters, ensuring uninterrupted power to our subscribers. Our system also monitors energy consumption. If a user exceeds their allocated amount, the system signals the utility to disconnect the excess load, ensuring fair usage. With an intuitive user interface, subscribers can easily track their energy usage and remaining balance, making Lifeline Power an essential solution for reliable energy backup.
Now, let's look at the Lifeline platform in action. We will provide a high-level overview of how a service provider and a consumer operates through our platform. The service provider can log in, select a transformer, and add batteries to it. They can then create packages by specifying the energy, power limitations, and etc. Now let's look from a customer's point of view. A customer can log in, they can view the status of their current active packages. They can also view their past purchase history and browse through available packages for purchase and buy them. Once a package is bought, their billing process will be initiated accordingly. Now, let's look at the forecasting model implementation. When it comes to efficiently managing distributed energy resources like battery energy storage systems, a forecast of the predicted energy usage can be really useful. Therefore, we have developed a forecasting model that predicts the day and hour ahead energy consumption. Time series data like energy consumption data is sequential in nature. Hence, we adapted a transformer encoder architecture. We feed in sequences of past electricity consumption data, which are first encoded with positional information. This is because transformers lack the capability to understand the inherent ordering present in sequences. The encoded vectors are passed to the encoder stack that comprises 6 encoder units. Each encoder comprises of a self-attention layer and a feed-forward layer. The self-attention layer uses multi-head attention with 4 heads. Finally, the output encoded vectors are averaged to form a single vector which is fed into a feed-forward network that outputs the energy prediction for the next time step of the sequence. Our goal was to deploy the forecasting model in an edge device so that inference can be done on the edge itself without relying on connecting to the cloud. This becomes important in rural areas where there is no guaranteed stable network connectivity. Therefore, we compressed the model to a more lightweight format suitable for edge deployment. We used post-training quantization strategy for this. The resulting quantized models were deployed in a Raspberry Pi for edge inference. The quantization resulted in a 70% reduction in model size, a 20% increase in inference speed, and only a 2% reduction in inference accuracy. Hence, the inference performance in the edge device was similar to that in a normal CPU GPU.